Victor? Hello. Here, one. A quick second. This guy real quick. Lord, that's your skull. Racer. Hey, Luke. I'm just getting out paper for now. Hello. Let's see if people can make it with that. So what were the results of the form? At least 6 people out of the 8 who answered from the 22 who answered originally can make it. Okay. I did say 5:30 though, so I'm gonna be in here for a little bit, but anyone who wants to join can join.
So a ganja, do you have a specific problem you want
Or
us to
question.
help with?
I just brought up paper with my calculator. Oh, there you go. Shoots. What time? Let's see. Thank God I was able to log on the ScioVirtual account because that would have been like kind of bad because they had to sign in and get a bunch of more information. Just really annoying.
See what this is.
What? Oh, start collaborating. Oh, notes. New.
No?
Can you see this? Here.
Yeah, I don't see it.
Share to meeting. Share note. You should be able to see it now. This side.
Yeah.
Yeah, you can see it. Also, I for the poll that I ran, right? People 66%, aka 4 people, answered yay to hype for German lesson with Luke. Unfortunately, Brendan was not able to make it today, probably, because he said he was
Yeah.
banking on the fact that it'd be like the other day, but then it wasn't. Akamsha, do you have any questions that you want to go over? And if you're talking, we can't really hear you. All right, chat maybe?
Hello?
Yeah.
Hello.
Hello.
Hello. Yeah, I can hear you.
Cool.
Do you have any problems you want us to look at together?
Um, the what's it called? The slides we did on Friday, the
Mhm.
mirror and the lens question. The bonus question
Oh
one.
yeah. Yeah, that's a good idea. So, what group are you in?
I think I was in two groups.
Uh, because I got a bunch of, I think I put them all in one place.
I sent it on Discord.
Mm-hmm. I know I have your groups. I have ray tracing. Let me see. I have uh uh lens system group 2, you said. I have group 3 twice. It's actually the same thing. Hold on, let me see it. I have group 5. Let me. Oh, are you the one who sent it to me on DMs? Yes.
Yeah, I am.
Oh, it's the copy of lens system. Yeah, I have yours. And
Yeah.
it's saved in the folder. I think I put it in twice. Oh, 2 people have copy of lens system. Okay, so I'm gonna rename this one group 2. So that here. What the heck? Give me a sec. So, because there are 2. Oh my goodness. Okay, my computer's just being extremely laggy. So, the bonus scenarios, right? Okay.
Yeah.
Yeah, so it wasn't exactly explicit how to do it. Why don't I just share my screen and then we can work it out on one specific. I'll just share the key. Give me one more second. There you go. And key lens systems. And there you go. There. Can you see my screen?
Yeah.
So this is what you guys did.
Yeah, this is yeah.
Okay, so that's interesting. That's an interesting scenario, but it's not exactly how you do it. So,
Okay.
you're not okay. So what we're gonna do for this is scenario 1, so we're gonna go to number 1. With a mirror and a lens, what you want to do first is you pretend that this mirror doesn't exist. And then you do the system just with one lens. And then say that gives you an image like here, just for now. Say it gives you an image here, right? Get rid of this lens and now place the mirror. And then you do it there and it gives you a second image. So
Yeah.
that's the general step. So you skip for one and then you skip one lens and then you go to the other. So let's see what we're given. We're given an initial object distance of 11 centimeters, given that this object height is 6 centimeters. So it's going to be like a little bit more than twice this. So we're going to put it like here. That looks about right. And then the focal length is 3.5. So let's pretend it's like right there. That looks about even, right? So first thing we do, I like to calculate it first, just to see what it's going to look like because the numbers never lie. So the 1 over f is equal to 1 over I plus 1 over p can just be simplified as SF over S minus F. So that's, by S, I mean object distance and F is focal length. 11 times 3.5 over 11 minus 3.5. That's 5.133333. So it's going to be a little over that somewhere, but we don't know that yet, so we're just going to ray trace. Let's go straight here. That looks about straight. And then let's go straight through the focal point. Right there. Let's remove this image. And now let's use our second ray. I don't know if I should draw all three if it's necessary, but
When I did it, I drew all three.
okay, let's draw all three then. Oopsies. There you go.
I think it's because you asked them to do all three
Yep.
rings.
I did. I was just trying to be a little faster, but I guess that's not the way. And now it went through the focal point, going into the lens, right here, and then grabbing on from here. Oops. Right there. So we already have a pretty good ray tracing diagram for our first image. And it makes sense, right?
Yeah.
So let's actually make this image a little bigger. We have that. We're going to scale it appropriately. And that checks out. Let's check for the magnification. Magnification, since the image distance is 5.133 and the initial object distance is 11, we have 5.1333 over 11, which gives us 0.46. So it's supposed to be about half the size. And when we put it right here, we see it's about half the size. So things match up already, which is really good. Does everything make sense so far?
Yeah.
Okay. So now we know that the separation between the lens and the mirror is about 15 centimeters. So we have, this is approximately 5.13. So this is approximately the distance that we need, right? So next thing we're going to do is we're going to grab our ray, have it straight, nice and parallel, even though it's supposed to be the same ray, but it doesn't matter. Oh, we forgot the focal point. Let's put the focal point on there in the focal point. Oh, oopsies. I used the wrong focal length for the lens, but it doesn't really matter. It's 3.5 for the mirror. That's my bad. Let me just redo that calculation with the correct focal length. That is completely my bad. It's supposed to be 44 over 7, approximately 6.2, and that's over 11, so it should be 0.57. If we move this down, let's just pretend like that was 4 centimeters. It's not going to affect anything much. But it's supposed to be 6 away, so it's going to be like around here. And then it's going to be a little bigger because the image distance is still higher. So if we pretend that that is 3.5 centimeters, we can take our rays, ray trace them, already traced actually. And now through the focal point, that trace this one from the image to this point, and then try to make that same angle of reflection here. What looks correct? Does this look correct?
Yeah.
It's supposed to be from the normal, so it's supposed to be something like that, I think. But let's see with the third one, the correctness of our middle one, because we can use that for correction. Use that, and then exiting parallel. Okay, so my ray of reflection was not very good because it crossed off here what it was supposed to cross off. A lot smaller, like this. And that even does look more correct on how it's supposed to be. It's approximate. Again, it's not always the same thing, but it's approximate.
Both of them are.
And now we can place our image down here at the appropriate height. Does this make sense using ray tracing?
Yeah, I just didn't know that I thought we were only supposed to make one image.
Yeah, so I think we hopped in between rooms to specify that this is how you're supposed to solve the two system images. Just make one image after the first lens and then another image after the second lens. All right, I'm gonna leave you a little challenge here. I'm gonna go back to your original slide, and I'm gonna ask you, can you calculate the right values now without changing this slide? Just essentially just redo it.
Okay.
Without the ray tracing, just for the calculations. Can you give me the correct image distance at the end and the correct image height?
All right. Wait, so the formula is 1 over object distance and then minus 1 over focal length equal
Oh,
and
here,
then
let me
inverse of
just write it
which-
out. I'll write it out here. It's a very important formula to have memorized. 1 over f is equal to 1 over I plus 1 over p, where I is the image distance and p is the object distance.
Yeah.
Ivan,
Hello.
there are two people here. Three.
Wait, you can attend with me.
Yeah.
The camera on का it says to eye contact or no?
There's no like attendance code here.
Okay.
So it's a based on a question basis. So the nice thing about this is that this equation can be rewritten as f is equal to sorry, my bad. Let me just rewrite this. It's not f. That's not what I meant to write. I meant to write I is equal to pf over p minus f. That's what I use to calculate the image really fast, because this is kind of annoying to deal with in terms of algebra. So I just rephrase it in terms of this, and this is the same thing. The only thing is that you're using a number twice, and so that's why we're not that's why it's not the proper equation form, because usually you just want to have one of every variable when you want to solve for things. But this is a pretty useful form to have memorized. All right, let me just calculate it myself. So Evan and Ethan, what we did was we went over how to solve this system, which is not exactly like this, rather like that. What we're gonna do is, for the first lens, for the first image, we pretend like there's no mirror after.
When we like find the image of the first lens, then use that as the object for a mirror.
Exactly.
Okay,
Exactly.
I did that for like the homework, the problem
I
set.
think I got it.
Yeah. All right. What did you get the same answers?
No, for image distance, I did the formula you did on the bottom. I did P is object distance, so 11 times 4 because that's the focal length.
11 times 4 over 11 minus 4, right?
Yeah, which is 44 over 7.
Yep.
And I got 6.2857142586.
Yeah. So that's the first image distance, right? Now we got to do it for the second lens, because this is that distance right here. What we just found is this right here.
Yeah.
Right? So now what we do for the magnification of the first one is we write m is equal to negative I1 over P1. And that's our first magnification, which is going to be equal to over 11, which is equal approximately negative 0.57, right?
Yeah.
So we know that our image is already going to be like diminished by negative 0.57, like a factor of negative 0.57.
Yeah, so you can just multiply 6 by 0.57. Yeah.
Yep, exactly. So this times h1, which is what we're going to call this, which in this case h1 is 6 centimeters. And that's going to give us our second object distance, technically, right? It's not exactly an object, it's an intermediate image, but we're going to use it as an object. So what do we know from this? What do we know from this value? Well, we know that 1, it's going to be around half the size. And 2, what do we know from this negative?
That it's inverted.
Exactly. So for our first image, is going to be inverted. That's a very important thing to note. It's diminished because this is under 1 and inverted. This is a very common case for the convex lens. Very good thing to have memorized. All right, so now that we have that, we're going to do it again. We know that the distance from here to here is 15 centimeters. So how do we know what is this? How do we know what that is?
Subtract like the separation of lenses by the from the first lens.
Exactly. So this first red thing is going to be 15 minus 6.285. That's our new image distance. So let's write that somewhere else. For number 2, P is equal to 8.714, right? Approximately, because we don't have all the decimals. And then F in this case is going to be 4. 3.5, sorry, not this. 3.5. So let's use this formula again, but this time it's going to be I2.
Okay.
So this minus 3.5 over 8.714285. Yeah. So that should give you like 5.849. I just rounded it to 5.85. Follow along? Did you get this value?
Yeah.
Yeah.
All right, good. And now for a magnification, because now we're going to call this M1 because it's the first magnification. Now M2 is equal to it's equal to H1, or sorry, H prime, because this is the second height. Sorry, what am I saying? Sorry. It's I2. Just erase it. I was getting us to the next step. I2, negative I2 over P2. So negative I2 is going to be negative 5.85 over, and our image distance, object distance was 8.714. So we have that is going to be equal to, negative 0.67, right?
Yeah.
So that's going to be over, that's going to be for H2, for the second height that we want, the second image height, it's going to be negative 0.67 times that height that we have for this image, right?
Yeah.
So if we look at some math globally, let's keep this, and I'm going to erase this to right here. We have H1 is equal to M1 times H, right?
Yeah.
And
Yeah.
H2 is equal to M2 times H1. So that's equal to M2 times M1 times H for H2. So we see here one of the relationships between the magnifications is that M total, the total magnification, which makes sense, is equal to the product of all of the subsequent magnifications. So M1, M2, and then like M3 if we had even more lenses, and so on and so forth, right? So that's one thing that is kind of fundamental. You won't be seeing like 3 lens systems because that's just not going to happen. it's just repeating the same process over and over. But if we had 3 lenses, we could have M1, M2, M3 for the M total. This is a pretty important relationship to have because you don't have to calculate the intermediary image height. You can just calculate it all at the end when you have the magnification. And I mean, it makes sense when you like increase by a factor and then increase by a factor again. How much have you increased in total? Well, the product of those factors. Does that make sense?
Yeah.
Yeah.
All right, cool. Any other questions about
No.
anything we've learned? This is supposed to be question based, so if you have any questions, shoot, and I'll do my best to answer them.
Anything on the problem sets?
Wait.
I think I
How do
said
you
something.
prove like the thing, like the formula of like the 1 over like focal length and like question 11 or something? Like question 11 was like on the problem set. Like it was like 11B.
The first one or the second one?
Like second one. Yeah, second was like the y, the or something.
Okay.
But it was
Let me
it was something
load
else.
the problem set. 11. This one?
Wait. No, I think it was number 10. Yeah, it was number 10.
What is the effective focal length?
No, not that one. Like the last question.
Wow.
Like the
Oh, this
last
one?
question. The last part of question 10. How is the equation used for this derived?
Oh, that's the one with the that's the one on the extra slide that we didn't get to in class, but
No.
it was like as a note on the shared problem set. It's gonna be similar triangles, but with an extra term. So what happens is when you usually have like 1 over f is equal to 1 over f1 plus 1 over f2, right? What you're gonna have, this is for like if you have 2 lenses like this, they're like, oh, not like that. This was supposed to be a question for like everyone who looked at the slides. Here. So if you have, and I drew it wrong again. I don't know the derivation off the top of my head, but I'm sure I could figure it out. Like if they're like close to each other, it's like this, right? But if they're not close to each other and they have a separation, there's going to be one more term that's added that's like f1, f2 over f1 plus f2 minus d, just from similar triangles and the addition of the stuff in between.
I think this needs
Here.
an understanding of thick lenses. So
It does, like, technically it's like the principal planes like this.
yeah. So I think we should I'll
Uh,
make something about thick lenses as an extra thing soon.
yeah. If you can't solve this second part, don't worry about it yet. We're probably gonna go over it at some point, and if we can't, that's a mistake on our part. We probably should have included something about that first. I think it was in lesson, what was it?
4.
Focal length. Yeah. 4. I think Luke added a slide at the very end of class. There you go. When you add focal lengths, we technically didn't go over the derivation. It was supposed to be like an investigative task, sort of. Sign convention, we didn't even go over this. But this is essentially how it's derived. And when you start adding something in between, you can think of it like a thick lens, and then you have more complications with traveling rays inside of the lens because it's not thin. Does that make sense?
Yeah, yeah.
So short answer is that's my bad. I included something perhaps that we didn't go over. Should probably delete that. But we'll add something to it soon.
Okay.
And then deriving this one is literally on the slides. It's like what all of this is. Were we able to do all of this?
Yeah.
This is a lot of this is the same thing over and over again, just
Yeah,
with different
yeah.
cases. Even this, were you guys able to use the thin lens? I
Yeah.
mean the
Lens
maker?
That was my no optics note, so yeah, I used it.
Yeah, that's good.
Uh,
Were you guys able to solve this one? This is a very interesting question.
That's the only one I haven't done yet.
So
Like, how?
the only thing that you need for this is actually the lens maker's equation. It's the exact same thing as the one before.
Like
So
the
if we give-
modified lens maker equation, but then like in the modified one, it's just like n1 over n2 and like -1 instead of like n1.
Yeah. So
But then like
the real lens maker's equation, the real lens maker's equation is 1 over f is equal to n1 minus n naught over n naught of 1 over r1 minus 1 over negative r2, right? The reason why we write this term as n minus 1 is because if it's traveling in air, n naught is equal to 1. And so this n over 1 is just like 1. So there's no point of putting it over 1. So we just change this to 1, and then this is supposed to be
but then like with that modified one,
so that's
I
why we
don't
write
know
it as a
wait,
simplified
for like the
version.
modified one, like it's like in order to find out like the focal length, you need to know the radii of curvature. So like see like in
So
the
you actually don't need to here, because you can use this information to figure out the focal length, and then you can use that to use the radius of curvature.
oh wait, the radius of curvature is the focal length. No, like
No. So
kind of not. Wait.
we know that let's find out what we know. Let's write out what we know. We know that the index of the lens n1 is equal to 1.5. And we also know that when you have a lens, if you just have this specific lens, no matter the radius of curvature, right? With like if we have like an image here, we're gonna have the same image right there from that, right? And we know that this is 18 and this is 24. That's what we know. So what do we know from this? What can we take away? Well, we don't exactly know what the focal length is here, right? But we know that 1 over f is equal to 1 over p plus 1 over I. And they do give us p and I, so we can figure out the focal length. So let's do that right now. If we plug it in to the equation, 1 over 18 plus 1 over 24, and then 1 over that, we get 72 over 7. Do you guys get the same thing?
Wait. Wait. I don't have a pencil with me right now.
Do you have a calculator?
Yeah, I can just use my iPad.
Okay. A calculator should be all you need. You don't really need a pencil for now. So from that, I'm gonna pretend like you guys did get that, right? Because it's just a matter of plugging into the calculator. And then now we know the focal length. So before we had two unknowns, we had this as an unknown, and we had this as an unknown as a big chunk. That's the key foundation to this question. We know that now 1 over that focal length, which is 10.286, is equal to, in this case, n minus 1, because we're in air, minus 1, which is just going to be 0.5, right? Times 1 over R1 minus 1 over negative R2. The interesting part about this question is that if we write out what it's going to be on the next one, we can think about it as 1 over f prime, because it's not going to be the same focal length, is going to be equal to n naught minus n1 minus n naught over n naught times 1 over R1 minus 1 over negative R2. So we know that this term right here is the same thing, right?
Yeah.
So we don't really need to find out what R1 and R2 are, because that's two unknowns in one equation. But we do know what they are together. Like, we know what this whole term is.
Oh yeah.
This
You
whole
could, like
term.
divide both sides by 0.5 and then find it out.
Exactly. So since this term is going to be constant, we're going to say let x equal to 1 over R1 minus 1 over negative R2. And then we can rewrite this as 1 over the f that we found, which is 10.286, is equal to 0.5 times x. Solve for x. We have a new problem now. Solve for x. And x is going to be equal to 1 over that divided by 0.5. 0.1944 for repeating, right? Did you guys get this too?
Yeah, I got that.
Right. So we know that this term right here is equal to 0.1944 with 4 repeating, just from that first equation. And so we can use that in our second equation, even if we don't have the radius of curvature. We know that what that term is equal to. And then the problem becomes a lot simpler. 1 over f prime is going to be equal to 1.5 minus 1.33 over 1.33 times our x value here, which is 0.194444 repeating. So let's put that into the calculator and find out f prime. 1.5 minus 1.33 over 1.33 times that term. And then 1 over that, because we want focal length. And we see that our new focal length is equal to 40.235.
Yeah.
So that is the key step. Figuring out this, that they're the two same term, and solving for it is the key step that we're going to use for this whole question. And now we have our new object, right? All we need to do now is just plug it back into the equation. 1 over f prime is going to be equal to 1 over p plus 1 over I. We have our p from here. all we need to do is calculate I. So let's do that right now.
I got the answer. I think
Which is
it's like 32.571.
negative 32. Very
Oh,
important negative.
wait.
0.571. That is correct. Or
Wait.
let's write it to 572 because
It was
we're
like that
rounding it.
formula earlier where you said like you should simplify it to like so like the image distance equals.
I is equal to SF
Oh yes, yeah. Oh wait, oh yeah. Oh wait, I
over S minus S minus F. So we can also find something new about this.
okay, I got it.
If we look at this simplification of the equation, right? I'll just rewrite the bottom. We find out another relationship between like for convex lenses and mirrors. We know that if the focal length here, let me just write it. We know that if the focal length is greater than the image distance, which means that it's within the focal length, we know that this term is going to be negative. And so we're going to have a negative I, which means it's going to be virtual. For a convex lens or a concave mirror, when the focal length is positive, we know that if the image distance is within the focal length, we're going to get a virtual image. And let's go over to PhET simulations, and we're going to look at this.
Yeah, doesn't like when it gets like when the object gets closer to the focal point for like convex lenses and concave mirrors, like the image gets bigger.
Mm-hmm.
Okay.
So let's look at this. I'm going to keep the writing for now, because we're going to go back to the doc. Look what happens. As we get closer to the focal point, the image comes infinitely far away. And here at the focal point, it's infinitely far away. All the rays are parallel, because if we put it right here, right, they would go parallel to the optical axis, right?
Yeah.
So if we put this image within the focal point, it's going to be infinitely far away. But as soon as we get within the focal length, we see, oh, we have some backwards ray tracing here, because now we're closer than the focal length. And so these rays are actually, they actually go outwards. It's like if they were going like this. They're diverging. And so this is a massive oversimplification of how much it bends. And we'll see how much it bends in a second. There. But now if we move this image closer, we see that it's a virtual image that's actually behind the image. And it happens, this little switch happens when we get through the focal length and into the focal length. It's a very interesting relationship. It's very important. If we go to look at a mirror now, we see that same thing. It's a real image up until we get closer. And when we pass the focal length, these rays diverge. Right now, it's infinitely far away from this side because we're at the focal length. And when we get closer, we see immediately a virtual image forms. And then it gets closer as you move it closer. Does this make sense?
Yeah. Wait,
Isn't it
like
cool how much you can tell from just a simple equation like this?
yeah.
From this relationship. Just by writing it out in another way, you can tell these things.
And for like question number 13, like do you just plug in the lens maker equations, or like instead of the radii of curvature, you put like a random number x or something, like an x, like just
So
and then
yeah,
if it's like flat, then you put infinity.
exactly. If it's flat, you put
And then if like the focal length's negative, you put diverging, and then like if it's positive, you put converging. Okay.
Exactly. You got it. That's exactly that. If you put in R1 and R2 for positive and positive meniscus lens, you would have to, if you didn't know how it is, and if you didn't know that it is converging, you would have to know that it's going to be a positive. You would have to look up the radius of curvature convention for the positive meniscus lens and the negative meniscus lens to know which ones are 1 and which ones are 2. Because for the positive meniscus, the greater this one is R1, and you wouldn't know that, and this one's R2. How do we know that? Well, if we know that it's converging, this one looks flatter than that one. Let's write this one. Here. This one. So if this one is flatter than this one, we know that the radius of curvature R1, or just R red, is going to be greater than R green, right?
Yeah.
So if it's converging, oh wait, did I say the wrong thing? Yes, it is. It's an inverse relationship. Sorry, this is R1, this is R2. Because when we write out our equation, I'm tweaking a little bit here. 1 over F is equal to this term n minus 1 over 1 over minus 1 over negative R2. But in this case, we know that since it's from the other side, they're both going to be a positive. And so we just need to put the right one into here to find that it's converging or diverging if you invert them, which is what happens with the negative meniscus. We need that term to be greater because it's a positive R2. Since it's a positive R2, we need this term to be greater so that this whole term is negative. And so we get a negative focal length. And you would find this out again from looking up the sign convention to find which one's which. Does that make sense too?
Yeah.
Yeah, pardon me, I got them wrong in the first place. There's something that I would sit down and just figure out. If you know how to figure out, it's pretty easy when you like get there.
Yeah.
I think this is pretty like fine to do. The
I
point
already
of this,
solved it.
huh?
I already solved all of the questions except for like the number 10.
Yeah.
Except for like the last part of number 10.
Yeah, the last part of number 10. Yeah. That's good. Any questions from problem set 1?
No, wait. Let me check.
Because I know no one got 100% on problem set 1. As the graded.
What is that? Let me see which ones I got wrong.
So
Transport.
yes, you could leave if you have no more questions. Sorry, I didn't see this.
He
Oh,
already.
he already left.
Yeah, I'm gonna check what questions I got wrong. Okay. Wait, how do you find out number 7? What do you do?
Number 7. I forget which one number 7 is. Is that the reflections one? Oh, yeah, that was a little bit of a hard question. So, let me share screen. So we have a circular pond. Actually, can I make a drawing screen here? Yeah, whiteboard, new whiteboard. Hopefully you guys can see this.
Yeah.
Yes. All right, nice. So First thing when you have these diagrams is you draw a diagram. Sorry, when you have these problems is you draw a diagram. So you have a circular pond of radius. Let's draw it with a radius like this, just is equal to 5 meters. And
And
it is 10 meters
He's in the
deep.
center, by
Yeah.
the way.
That is not drawn to scale. Let's try to draw a better picture. Where's my pencil? What the heck? There we go.
Maybe just do a cross section.
Yeah. So now we don't need the circle anymore because we understand like the problem, right? This is like the pool, and the guy is right here.
Yeah.
We know that the guy's right here, so now we don't need this anymore. We don't need the circle anymore. First thing that we can notice is the maximum angle that we're going to be able to see at from this pool is by looking directly from here all the way up to here. And Lucas is drawing the rest of the diagram here. You have a distance of 7, yeah, and then a tree of 8, exactly. So now our question is, does this, when we get out of the pool here, we can extend the normal. Does this ray hit the tree or hit under the tree?
Or
Under
over
the top of the
tree.
tree. Yeah. If we can see that this ray hits the top of the tree or under the top of the tree, we know that we can see the tree. And if it goes like here, then we can't see the tree, right? Because the tree doesn't go higher up than this. So this is a case where we can't see the tree, and these two are cases where we can see the tree. So let's calculate something here. We first want to know the angle of incidence, because we're going to leave, this is the observing eye right here. The eye is right here. Right? Pretend like that's an eye. Eye is observing from this point right here. So we can find the angle of incidence, because this one is the same as that one, because they're inter-alternate angles. So we have that angle with inverse tan of 5 over 10. Right?
Yeah.
So theta 1 is equal to tan inverse of n2 over n1. Sorry, tan inverse of, that's another the y over x. So 5 over 10.
Wait, do you know how trigonometry applies to triangles?
Yeah, like so contour like that.
Yeah.
Yeah.
So we know that if we have that triangle right there, right? If we have this angle theta,
Yeah.
SOHCAHTOA, we know tangent is equal
It's
to opposite over
adjacent.
adjacent.
Yeah.
So opposite
And
over adjacent. And so since we're taking, this is tan theta, so theta is equal to tan inverse of opposite over adjacent, which is right what we have right here. If we have pictured this triangle, this is also 5, because that one on the top is 5, and this is 10. So tan inverse of opposite over adjacent, or y over x. And that gives us 26.565. Next thing that we do now is we calculate the angle of refraction. So we have n1 sine theta 1 is equal to, and since the second medium is air, just that's n is equal to 1, so sine theta 2. And so I'm going to let you do the math. I'm not going to write it out because I hate writing with the mouse. But it's sine inverse, oopsies, sine inverse of n1 sine theta, so 1.33 sine of what we just found. that is going to be, let me just erase this, right? That is going to be 36.49, right? That's what I got.
Yep.
Let's just draw this right like this, because we don't know where it's going yet. We know that this angle is theta 2 is equal to 36.497. 498. I'm gonna keep it to very high depth here. So now we need to figure out if it touches the tree. One approach, there are two approaches you can do to this. One is you can just figure out how high the tree would have to be for the ray to hit the tree in terms of given that you have the angle, how high does the tree have to be? Or you can figure out, is this angle that we have from the angle of like refraction, is it bigger than or equal to the angle that we need? Not the critical angle is poor phrasing because that's another technical term, but the minimum angle that we need for this ray to happen. Let me just change colors. This one, which goes right there. If it's plus 1 alpha, if it's greater than or equal to alpha, then we know that it does. You do see. But if alpha is greater than theta 2, then we know that it's no C. We don't see it, right? So we can take that approach first. And to calculate this critical angle, right? We know that this is 7, this is 8. So we have this alpha is equal to tan inverse of 7/8.
And then that's like 41 point something.
Which is equal to, yeah. So let me just type that out. 7/8. It is indeed 41.18. Or 19 if we round it. Right? And now we can check this condition. Is 36.498 greater than or equal to 41.19? Nope. So we can't see the tree. Does that make sense?
Yeah.
Now let's look at the other approach, which was Luke's approach on the answer key. He actually calculated how like the minimum size of the tree that we would that it would have to have if we were to see it. So given that we have this angle, and I'm gonna go back. Given that we have this angle, we know that the minimum height x. Let's rewrite this as x here. The minimum height x that would have to be, if we write this triangle out, so this is x2. We have tan of theta 2 is equal to 7/x. So if we solve for x, that's equal to x is equal to 7/tan theta 2. This is the minimum size of the tree that it would have to be for us to see it at that place. So 7/tan of theta 2 is equal to 9.46. This is the minimum height for us to see it. And we know that the tree, the actual height, is equal to 8. So since 9.46 is greater than 8, we know that we can't see the tree.
How do we solve for like 7/tan theta?
Oh, so this is again the same trigonometry that we have here, right?
So good,
If we
Tyler.
have this being a right triangle, that is a terrible right triangle on my part. Let me just try to draw it again. Right? If we have this, which is just that triangle here, rotated clockwise this way, right? By 90 degrees. We have sine of we have tan of theta is equal to opposite, which is here. Let's call that y. Opposite over adjacent. Let's call that x. Does that make sense so far? Just the trigonometry part?
Yeah.
Opposite over adjacent. And so now we just multiply both sides by x. So we have x tan theta is equal to y. And then we divide both sides by tan theta. And we have x is equal to y over tan theta.
Oh wait. I actually was asking about like how did you get 9.46?
Oh, by just plugging it in. 7 over tan theta 2, and we have theta 2 right here.
Oh, okay.
Because that was
Oh wait, wouldn't just oh wait, no, it'll take the same amount of time to do it. Okay.
that approach was based on the angle that from that angle, what is the minimum size that we have to see? Questions?
Wait. How do you do number 8? Like the
Number 8.
into that.
Okay, so you do it like this.
You
What
got
was the
this one,
original
Luke?
answer you got?
I don't know. I just didn't know, so I just guessed on it.
All right,
Can I
Luke, you
clear
got
the
this
page?
one. Yeah, go ahead, clear the page.
Okay, so oops. So over here, we have our mirror, right?
Yeah.
And what you should never do is never assume that the diagram is up to scale. So always just use the numbers they give you. Hold on, let me just get back to the problem set. So the initial incident angle is 86 degrees, right?
Yeah.
Yeah. And the original angle of the hemisphere it hit at was 15 degrees, right?
Yeah.
So let's consider what happens when it reflects off the surface. So let's say it goes here. So what do you notice about this triangle over here? Like, are any of the do any of the two sides have equal lengths?
Like one of them do.
Which ones?
Like the middle one.
This one
Wait, the one
and
to the
this one?
yeah, the one yeah that wait, the one to the right of the one you're looking at right now.
Yeah.
Yeah, one.
So this and this, right?
Yeah.
And what's the angle here?
86.
Yeah, because of the law of reflection. So then, since these two, this is an isosceles triangle, this one must also be 86 degrees, correct?
Yeah.
And what's the value of this angle?
Like 180 minus 86 minus 86 again.
Yeah, so If I'm not wrong, that's 8 degrees, right?
Yes, 8 degrees.
So then let's see where this ray goes after it reflects again. What do you think? What can you say about this triangle? This new triangle I created?
Probably also 86.
Yeah, so so as you can see, we're creating the same triangle multiple times as it reflects.
So it's yeah, and then those two triangles are conjoined.
Exactly. So every time it reflects,
And then you can just like add like 15 and like you gotta start from like you just keep adding 8 and like which is like 180 or something.
exactly, yeah. So we have our equation. So how can we put this into an equation where we can solve for the number of bounces?
180 equals like 15 plus 8x plus 8x or something like that.
Yeah. 180 equals 15 plus 8x. And so what's the nearest integer? What's the highest integer that you can plug in so that 15 plus 8x is not greater than 180?
20.
20. So that's our answer. X equals 20.
And how do you do number 12?
Number 12.
Yeah.
So that's the fiber optics one, right?
Yeah.
Okay,
Can I
I'm
get
gonna
this?
clear
Can I
this,
get this
right?
one?
Yeah, sure. I'm gonna clear this in
Yeah.
3, 2, 1.
That was a great problem, by the way. Luke, love that problem. Um, let me go to the fiber optic. What is the number of the fiber optics one? 12?
Yeah.
Okay.
Light
Well,
enters a 3-meter long fiber optics cable.
all right. So there you go. So light enters at 3. We know that. Let's just write down what we know again. Einstein's done this. Length is equal to 3 meters. Angle theta I is equal to 25.45. Fiber optics core is core, we're just going to call it N2 is equal to, we said 1.52. And the cladding, which is what's around the core, is N3 is equal to 1.343. So now we're going to draw a picture. Well, we already have a picture, but we're going to draw a better picture. We're going to draw our own. So,
Arthur, I think you got this. I have to go now. Bye.
yeah, I got it.
Also, bye, Evan and Ethan.
How about
Bye.
Bye. Bye.
so? Let's keep drawing this. The funny thing is we don't even need the diameter of the. Oh, sorry. We have, for now, we don't really need it for the picture we're drawing. This, we're going to picture this, the entrance like this for now, and we're going to draw a clean. This is like the entering of the fiber optics cable, right? It's round, diameter 1 centimeter. So we're gonna rewrite this now as. Where's my pencil? Where's my pencil? There you go. Like this. And this is a new medium, and this is going to be like the middle. This is the normal. So we know the angle of incidence. That's going to be theta I. First thing that we're going to do is calculate the angle of refraction to see how much it bends in the medium. Second one we're going to do is check if this angle right here is greater, alpha, is greater than or equal to the critical angle. Right? So it's going to be sine of n2 over n1. If it's greater than that, then we know that we're bouncing at least. So that's going to be the first step to what we're going to do. So let's do that. Let's use Snell's law. N sine n1 sine theta 1 is equal to n2 sine theta 2. To find that theta 2 is equal to, and let me just calculate myself. It's sine of 25.45 over 1.522 instead of the inverse sine function. And we know that that's 16.4. 16.4 degrees. That's this angle right there. And now we know that this is 90 degrees. Right?
Yeah.
So what's this angle alpha?
That's like 90 minus 16.4.
Exactly, which is 73.6. Alpha is equal to 73.6. And now let's calculate the condition. Sine inverse, so this would be sine inverse of n2 over n1. Where's the sine inverse? There. Of 1.343 over 1.522. It's 61 degrees. So that condition is indeed met. And we know that we're going to be bouncing inside of the fiber optics cable. Right?
Yeah.
So now let's extend this picture all the way through. And we know that this is going to be some length L that we have. The first thing that we can do to find the number of reflections inside of the things is we can find one. We can think about what is going to happen after our first reflection. Can you tell me what's going to happen after here?
It's gonna like bounce off, like
It bounce off at the same angle, right?
yeah. And
It's
then
going to bounce off at the same angle, and then it's going to keep going, right?
yeah.
Pretend like this is a straight line. I did my best. I'm not very good. And then when we're here, what's going to happen here?
It's gonna bounce off again.
Exactly. There you go. Now, let's think about this for a second. What is that angle? That's alpha, right?
Yeah.
And now let's draw here a normal. What's that angle?
90 minus alpha. 90 minus alpha.
Not exactly.
Alpha.
This way. Yep, still alpha. And we know what this angle is, right?
Oh wait, oh yeah.
Alpha. So
Keeps bouncing.
So it keeps bouncing in a way that we can predict inside of the tube, right?
Yeah.
So now let's think about what we have again here. We know that this triangle is the same as that triangle.
Yeah.
Which is the same as that triangle, which is also the same as that triangle. And we know that after four reflections, the pattern repeats itself. Sorry, not after four reflections. After four of these triangles, which is two reflections, the pattern repeats itself. So now we have to find out, well, how much does one of these patterns take? Because if it's periodic like this, right, we can just divide this whole length of the whole tube, like this length divided by how much it takes for one of these periodic lengths. We're going to call that small l for this whole thing, is going to be equal to 2 times the number of reflections, right? Because there are 2 reflections per period. Right? Does that make sense? Okay.
Yeah.
So now we have this triangle, which we have to solve for this specific side. Let's draw that triangle a little bit bigger so we can see. We know this again is 16.4. We know that this from the diameter, which now we can pull in, the diameter of this whole thing is 1 centimeter. Right? It's 1 centimeter. So we know that this radius is 0.5 centimeters.
Wait, when it says like the diameter in the problem, it says like a 1
It's
centimeter.
this.
Does it mean like the diameter like inside, like not including the cladding, or like?
It's this.
Okay.
The entrance. It's how big. Pretend like this is the like inside of the cable and the cladding is like around it.
Yeah.
This radius of the inner circle
Okay.
is what's 1 centimeter of diameter. So this small distance here, this is 0.5 centimeters, right? Over 2. And we know that this is 90 minus what we had, which was 73. Which is equal to 73.6, and we know this is 90. So that's already a right triangle. We can solve it with our best friend, tangent. Tangent of 16.4 is equal to 0.5 over x. Let's solve for x. X is equal to 0.5 over tangent of 16.4, which is equal to 1.6988, a couple more. And we're going to keep it as all these decimal places because it's going to come down to precision to exactly how many bounces we have. We have this. This is how long one of the 4 triangles is.
So then you just divide. Wait, is that then you divide like 300.
And now we divide 300
by that number.
By 4 times that number because we want to see how many periods there are.
Yeah, 4.
The thing is, since there's not a reflection every time there's a triangle, because there are 2 triangles in that length, so we only have a reflection after the first triangle and the third triangle in that period, right? So that was the whole point of seeing the whole period, is that every single time we have a period, we know that there's 2 reflections. If we just went off the triangle, we'd have to think, well, it's after the first one and after the third one, after the first one, after the third one. And so we can't really divide by the number of triangles without making sense of that first, right?
Yeah.
So let's divide it by 4x. 300 divided by 4x. 4x. Oopsies, I did not put that. Divided by 4 times that number. That gives us 44.147. We know that we have 44 full periods, 44 full reflections, and then we have 0.147 of a reflection. So already we know that we have 44 times 2 bounces, right? 2 reflections, because 2 reflections in a period and 44 periods. So we already know that we have 88 reflections. The answer key might be wrong because I might have written 89 because of rounding. We have 88 bounces.
Wait, wouldn't it be, is it 88 or 22? Because like, wait, can you go back to like the equation of like the L over small l equal
L over this small l is equal to like 2 times the. So this only works when it's like even. In this case, it's not an even amount. So if like this, if the whole thing is like 2 and if the whole thing is 8 and every single one of these periods is 2, then we have 4. So 2 times 4 for the bounces.
Wait, what was like the equation again?
It was like a visualization thing, but the word, it's not a real equation.
That was 22 though.
Huh?
That would be like 22.
It's just don't worry about what I had written earlier. It was just a visualization thing more than the equation itself.
Okay.
We're not gonna be.
Oh,
yeah.
I see now. Oh, I see.
Yeah, it was just a way to say that like when we divide it, we're going to be able to find the number of reflections.
Okay.
If we have like reflections at distance of the whole thing. So now we have how many periods there are, right? We know
Yeah.
that there are, if this is one period, there are 44 of these guys repeated over and over again.
Yeah.
And we know that there are 2 reflections per period, so we know that we have at least 88 bounces. But we have that short decimal here, right? So do we have another bounce from this?
No,
Why?
because like when you multiply, no, when you multiply 0.147 by 2, it doesn't equals 1. It's less than 1. So that wouldn't add up to another bounce.
It's not exactly like that. It's more of you have a reflection at 1/4 of the bounce of the period and at 3/4 of the period. So when you have a fraction of a period left, right?
Yeah.
You have a reflection 1/4, which is 0.25, and then you have another reflection at 0.75.
So then.
So if this decimal was like 0.32,
and then.
if this decimal was like 0.32, then we would have one reflection. If this decimal instead was 0.86, we would have both reflections in, even though we can't finish the period. But here, since 0.147 is smaller than 0.25, we don't have enough space for one reflection. And the end of the cable is going to look something like this. If we have the end of the cable like that here with our normal in the middle, we've just finished our period right here. And then we have this. And then that's the end of it. That's the end of the cable. It doesn't actually finish the oscillation or period.
Okay.
It would have to be extended just a little bit to bounce off, but the cable's not big enough, large enough. Does this all make sense?
Yeah,
This is a bit of a hard problem.
it makes sense.
This is a division C problem that I put on another test. So
But like
it's
don't
supposed
you
to
use
be.
for division C topics and like division B anyways in optics?
Yeah, this is just the law of reflection and then the critical angle. You don't even need the critical angle because that was just checking a condition. It's literally just the law of reflection and the law of refraction with a like bunch of math. Problem solving.
Okay.
But that's what we do these, right? It's just for practice. Anything else you want to go over before I may have to leave in a couple minutes?
No.
Anything we left unclear in class?
No.
All right. Well, I hope I was worth your time.
Okay.
Thank you very much for
Thank
joining
you.
and asking questions. There's nothing better at the end of the day for me to think, oh, well, I helped someone understand something today. So, thank you.
Thank you.
Bye-bye.
Bye.
Bye.